Okay, for today's class activity, we're covering Chapter 12, Sections 10 through 11. Go read those sections, study the concepts thoroughly and practice with the concepts on these problems. Okay, and then this video, we'll come back to the video for some guidance to get through it. So looking at concept question 12, this is a fun one. So there's a pike position and a tuck position in diving. A pike position, the diver they're kind of in a just bent at the hip, so their feet are like this and bent and holding their ankles like that. Okay, and in that position, it's possible to get one, maybe 1.5 turns as they dive. Okay, so they're trying to do some flips, but in order to get more flips, they have to really tuck in. So the arms are around the legs there, and they're tucked in really tight, and they're trying to get 3 or more flips out of it. Okay. Question is why? Physically why? What does physics say about that? Okay. So momentum is conserved. Angular momentum is conserved. Okay. Now angular momentum is defined in magnitude as I omega. Okay. Now, if we think about the angular momentum of this case versus the angular momentum of this case, when they bounce off the diving board, they have the same momentum, therefore same angular momentum. And so when they pull into this position versus this position, that should be conserved. So think about when they pull into this position, how is this position different than this in this equation? Well, the mass is extended far out from the center of mass. Okay, the center of mass may be somewhere around like right here. Okay, center of mass may be somewhere around right here. But notice all of the mass is close by in this case. So if the moment of inertia gets smaller by pulling the mass closer in, okay, and that means that the speed of rotation must increase. So because momentum is conserved, this one would be a faster rotation because you've decreased your moment of inertia. All right, 13. Okay, we have 2 different disks. Okay, and we're trying to figure out how the moments of inertia compare. So angular momentum is defined as I omega, and I for a disk is 1/2 m r squared. Okay. And so in disk, we'll call that A. All those are referenced to A. In disk B, okay, it's the same mass, but it's twice the radius, and it's 1/2 the angular speed. Now the radius matters most because it's squared. So squaring the 2, we get a 4. Dividing by the half, we get a 2 overall. That gives us twice the angular momentum of A. Okay, so though it's spinning half as fast, having twice the diameter makes a bigger difference. Okay, let's take a look at 37 from the text. This is practicing with just general cross products, since we're learning about cross products. Okay, how do we apply it? So we have a couple different scenarios. We have a vector A that goes like this, and a vector B that goes like this, and we're given this angle, which I'm going to call phi. So this is B, this is A. We want to find A cross B. How do you find that? Well, it's going to be A times B times sine of the angle between them. Okay. Now the angle between them is not phi. Mathematically, you'll get the same result if you use phi in this case, but you just do need to be careful. But just to be explicit, I'm going to extend A out. So you notice A is pointing that way. So you want these to have their tails together. So this would be A. I just moved it over here so their tails are touching. That is the angle between those 2 vectors. So you need to be careful when you say sine of theta. Well, what theta? You have to make sure you don't just write down whatever theta is on the page. It's the angle between those 2 vectors. when their tails are touching and they're pointing from each other. Okay, now in this case, you'll get the same thing because sine of theta, all it cares about is how perpendicular B is to A. So I could write this as A, B perp. Well, B perp is this much, and it just so happens that sine of this angle gives me the opposite side, which is this much, and that's going to give me the same amount. If I did sine of this one, I'd also get this much. It doesn't matter. Okay? But thinking about it physically is critically important. All right, so if you plug in size of A, size of B, and take sine of the 45 degrees that's given, you'll end up with about 17. Okay. Now, question is, what direction will this point? The way these two vectors are oriented, okay, if we use the right-hand rule, okay, the first vector points that way, the second vector points that way, and my thumb is constrained to point out at you. So the full answer here is this is out of the page. Okay, again, I put that little hat. That's a hat to mean direction. So it's size of 17 out of the page. And it gives me a full vector form. Well, that's A. Now let's try C or B as a vector C pointing that way and a vector D pointing this way. And what is C cross D? Well, technically it's CD sine of the angle between them, but the angle between them is 180 degrees. They're pointing opposite each other. I can put D's tail right here, and the angle between them is 180 degrees, which gives me 0. So again, thinking about that cross products all look at perpendicularity, these aren't perpendicular at all. There's no bit of this that's perpendicular. They're parallel. So I get no cross product. Very good. Let's take a look at 42. Okay, this one is defining angular momentum, and we're looking at a particle, so we use the particle form. Okay, we have a particle that's sitting here at 2 and 1, and that is in meters. And it's moving down and to the right, an angle of 45 degrees below the horizontal. My question is, what is the angular momentum of this particle? It's a 200-gram particle. So what is the angular momentum of this particle? All right, since it's a particle, then I'm going to use this definition of R cross P to find that. Now P, I can see P, it's mass times velocity, and its vectors pointing the same direction as the velocity. Well, what is R? What's the definition of R? Well, you'll note in the problem that this says the angular momentum about the origin, or with respect to the origin. Remember, just like torque, it cares about where our choice of a pivot is. And so this problem tells us we're going to choose the origin as our pivot, or the point about which we're measuring the angular momentum. So we always have to take that into account. Okay? So if I call that point A, sometimes I like to write this R or LA, meaning it's the angular momentum about point A, or with respect to point A. Okay, well in doing this, this is just going to be RP, sine of the angle between them. So I have to draw R. R is going to look like what? So R points from the reference point to where the particle is. That's R. Okay. Now what's theta? Is that theta? The answer is no. That is not theta. Okay, so I'm actually going to be more careful. I'm going to draw that as phi to keep theta in my equation. I'm going to redraw those now. I've got R pointing like that, and I've got P like that, and theta is the angle between them, which is made up of this angle and this angle, which I'm going to call gamma. I like to use Greek letters for angles. And so to find theta, I need to find gamma. I already have phi, that's 45 degrees, so I need to find gamma. And so how can I do that? What here gives me information to find this gamma? The answer is this gamma is the same thing as right here. Okay, because if this is a horizontal line and I'm measuring up to r, we're horizontal line measuring up to r, so I see gamma right there. So this is rp sine of gamma plus phi, and gamma is going to be inverse tangent of opposite, which is length 2, over adjacent, which is length 1, so 2 over 1. And so now I can solve for L. Plugging all of that in, you get L equals 1.3. Now, here's an interesting thing about units. What is L? Well, momentum is kilograms meters per second, and position is meters. So the units for angular momentum are kilograms meters squared per second. Okay. Now, I'm not done, because I found out how big L is, but I haven't found its full direction. So in this case, I got to use the right-hand rule to get that answer. And so here's my fingers in the right-hand rule form. And again, I like to choose this finger to be the first vector, which is R. So I'm going to point in the direction of R. It's up like that. Okay. Now to get V pointing the other direction, I got to turn my hand over, keeping R pointed up that page. Well, V is that way, which you can't see my thumb. Here's my thumb. Thumb is pointing into the page. Okay, it would be out of the page if P was the opposite direction. But to get my V in the right direction, it's into the page. So it's into the page. Okay, very good. Now let's look at 43. Okay, so 43 is another angular momentum definition problem. Okay. We have a disk that's spinning. Okay, spinning this way. And it gives it, with the axis of rotation being the x direction. Okay. And z's that way. And z, and this is y. And it's spinning in the YZ plane, so the axis of rotation is the x-axis. And we're given an angular speed, and we're given a mass and a radius of this disk. So we're given m and r. So what is the angular momentum of this disk? Well, I could use this one here, but I'd have to integrate it for all the momentum of every little piece of mass along this. Which, if I do, I just end up with L equals I omega. Okay, which is pretty cool. It's pretty cool that that's how it ends up being. So instead of doing this every time, I can just find I for a set of common geometries, which we have a table for that, and then find out how fast it's spinning. And so we have that. And so for a disk, that's 1/2 mr squared. I've got all that. I can calculate that. And omega, it's given in revolutions per minute, which I'd have to convert to radians per second, doing our proper conversion. But now if you do, you'll get an answer of 0.025 kilograms meters squared per second. And let's check those units again. We should get the same units, but is it the same units? We got kilograms meters squared, and omega is radians per second. So radians isn't a true unit. So it's kilograms meters squared per second. So it's the same thing. But we're not done. What's the direction? Okay, by the right-hand rule, I could pick any point. Okay, I could pick any point. Let's say this point right here. I'm going to pick a point right there. So at that moment, the velocity of that is this way. The momentum and velocity of that point right there is in the y direction. Okay, so if I'm going to do my cross product, r points from the axis of rotation up to it. P is that way, which means my thumb is constrained to point into the page. So I get into as a direction. Now, often for rotational things, it's easier to use a different right-hand rule. Okay, that's this. Your thumb is a straight thing and your fingers can curl. Okay? And what you do is you curl your fingers in the direction of rotation and your thumb will point in the direction of the cross product, or in this case the angular momentum. And so this thing is curling this way, which means my thumb is constrained to point down or into the page. So this works pretty good. It does the same thing, but it works pretty good for extended objects. You can still do this as I already did, but this also works if something's a larger extended object. You say, okay, well, what direction is it rotating? Curl your fingers in that direction, and your thumb will point in the direction of the result of the cross product. In this case, that would be L. Excellent. Last one. 89. Okay. Now 89 we're going to do, ask it a little bit differently just to keep the math a little bit simpler for this discussion. But what we have is we have a rod that's pivoted about its center, hanging vertically. Okay. So if I were to push this up to here, it would swing back down because it would be under the influence of gravity. Actually, I take that back. It wouldn't in this case because it's pivoted in the center, because gravity only acts on the center of mass. Okay, but gravity is pointing straight down, so G is down. Okay. Now, it sits barely not touching a frictionless surface, and I have a blob of clay that's traveling towards it with some speed v. Okay, this thing has a mass of L, or a mass of 75 grams and a length of 30 centimeters. This blob of clay has a mass of 10 grams and it's got an initial velocity of 2.5 meters per second. Okay, all those are given. Now the question, which I'm going to ask, is how fast is this rotating after the ball of clay hits and sticks to it? So what is the angular speed of this system right after the collision? How are you going to do that? Okay, so the idea is that momentum's conserved and angular momentum's conserved. So by doing this, I can say that the, or I should say angular momentum's not, in this case, momentum's not conserved, because in this collision there's a significant impact from the pivot keeping the linear distance from changing, or linear momentum from changing. Okay, so angular momentum is conserved because it's a collision about a pivot point, so we can say L initial equals L final, because there's no significant external torques about that pivot point. There's a significant force at the pivot point, but that's at distance 0 from the pivot point, so it has no torque. Okay, so we can say angular momentum is conserved. In doing that, initially we have to ask, okay, what's our initial angular momentum? So think right before the collision, this ball is basically at the bottom of the stick, straight down. Okay, so my R vector is straight down and equals L over 2. And P is straight to the right. And so those are perpendicular to each other. And so I can use the point particle definition of angular momentum for this. Now the rod's not moving at all initially. So in my initial case, I just have R cross P 0. And that's going to equal my final. And in this case, R is going to be L over 2. And P0 is going to be just the mass times V0. Okay, now I've chosen to call this positive, which means this would cause it to rotate this way. So I'm calling counterclockwise to be positive. It doesn't matter which one you do as long as you stay consistent from there on out. Okay, so if I call that positive, then this has a positive angular momentum. Another thing, really hard for me to do it, but if I were to point my first finger down, okay, my next finger will point in that direction for the momentum, which would mean my thumb would point upwards. Okay, and that's the same thing as this counterclockwise, thumb would point out of the page. Okay, but right now all I need to do is get positives or negatives. And so I'm going to define this counterclockwise to be positive, so that's positive. So now let's look at the final case. Well, now this is stuck to that, and this whole thing is spinning as a large extended object. So now I need to use I final omega final. Okay, I'll use this definition of angular momentum since it's an extended object. Now I final is the combined moment of inertia for a rod pivoted about its center, which we have in the table, and a point mass at distance L over 2 because it's stuck to the end. So I have to add it to the general one. So that's going to be, the rod is 1/12 m L squared. I looked that up in the table. That's pivoted about its center. Plus the moment of inertia of point charge, or point particle, is just the mass times the distance it is away from the pivot point, which is L over 2 squared. Okay. So let's just really quickly simplify that moment of inertia. Okay. See, an L squared is going to come out. I see a 1/12, and this will be a 1/4 once I square that half. So I'm going to pull a 1/4 out. That'll leave me with a 1/3 there, because 1/4 times 1/3 is 1/12, times a big M. I'm going to pull the L out on the other side. And if I pull a 1/4 out, that's the same as this 1/2 squared. And so I'm just left with M, and this L squared's outside. So I just kind of simplified this to get a fraction, a sum of masses, and the length squared. And that's all times omega F. So, in doing it that way, it allows me to do a little bit of simplification. 2 cancels with that 4, leaving a 2 behind. This L cancels with one of those L's. And that's about all I can do. So solving for omega final, I have mv0 divided by 1/2 1/3 big M plus little m times L. If we think about this, I have mass divided by mass, so kilograms cancel out. I have a meters per second divided by meters, so I'm left with the 1 over seconds, which is the correct unit for angular speed. So I've got this one, and if I plug in my numbers, I'll get 4.76 radians per second. Okay. And that's not very fast. That's not very fast. Remember, there are 2 pi, or around 6.5 radians in a full circle. So this is moving less than 1 full revolution per second. Okay, which seems reasonable. It's 75-gram rod is not terribly heavy. The 10-gram ball of clay is not very heavy at all. So it shouldn't get going too fast. But this seems to be a reasonable speed. Okay, so what we did is we used conservation of momentum to find the final velocity of this after it impacted. Now the actual problem says, how high does this go after that impact? Now to do that, we could use conservation of energy and a bit of geometry. The energy is not too bad because we now have a speed of rotation. We have a moment of inertia. We have a moment of inertia for this extended object. So we can have a k rotational gets turned into an mgh. Now that mgh is only for the point mass because this is the center of mass of this one is about its pivot point, and so it's not changing. The center mass stays there for the rod. So only this mass goes through a height h. So it'll end up at some. There's that blob of clay right there. And it used to be dangling down like this. And so it went through a height h. And so we'd have to use some geometry to figure out how the height compares to the angle. And then calculate that angle, which is what the problem asks for. But the most important thing is that we're using conservation of energy. The kinetic energy of rotation right after collision gets turned into gravitational potential. And so I'm going to leave that off because the math is a little bit complicated with this height change. But we could conceptually do that problem.